Hello friends, welcome back to Quantum Quandary. Um, right now I have a series in mind, one where we'll tackle the delta function. So as you might know, the delta function is the unique function, or mathematicians call it a distribution, because it's technically not a function, but we don't care, which is 1 at x equals 0, so when the argument is 0, and 0 otherwise. Actually, not 1, infinity. There's a small difference there, right? And 1 is the integral of the delta function over dx over, well, from minus infinity to infinity, or just from, let's say, minus epsilon to epsilon. The integral is the same because it's only 1, well, it's 0 everywhere else except in this one spot where x is 0, and that is 1. The integral of the delta function is 1. Okay, and now we're going to show why this holds, and we're going to show how the delta function can be defined. Okay, so we're going to start from a rectangle, or a function that is a rectangle. We're going to call this minus a and a. This is x, and this is f of x, or y, or whatever. And the amplitude here is going to be 2a, okay? Why? No, 1 over 2a, pardon. Why did we choose this? We chose this so that the area of the square would be what? It's the bottom side times the height, right? So that's 2a, that's the interval, times the height, 1 over 2a, that's 1. So this function has an area, well, the area under the graph of the function, right, which is just a constant, obviously, in between minus a, and it's 0 otherwise. Let's just write that. So f of x is 0 when x is greater than a, and 1 over 2a when x is less than a by modulus. Okay, so the area is always 1. That's what we like. Now, if the area is always 1 for this function, regardless of a, we want to have some sort of distribution that only exists in one point and is 0 otherwise. So if we want that, well, the area of this function, dx, f of x, we want that to remain 1, right, over the entire interval. You notice that this minus infinity to infinity collapses to minus a because it's 0 otherwise. So now f of x is just 1 over 2a, right? So it's 1 over 2a minus a to a dx. Okay, so this is what the delta function, this is what the area of the constant, under the constant from minus a to a is. And if we want the delta function, we just use the limit of a goes to 0, right? So we squeeze this rectangle. So what we would get on a graph, so we started out with this from minus a to a, and then we squeeze a, but such that the rectangle has constant area. So what we end up is this thing that we mark exactly like the arrow on the axis, unfortunately. Well, let's forget that the axis was there, and this is the delta function. It has width 0 and height infinity, but the 0 and infinity are in such a relationship that they equal to 1 when they're multiplied. You know that 0 times infinity is not generally defined, but this one obviously is, because what we have the limit of this as a goes to 0. Well, that's just 2a over 2a, and that's 1 with the limit. Even without the limit, it's 1, right? So then delta of x from the definition of f of x is just 0 when x is greater than 0, which is always, right? Except in this discrete spot when x is equal to 0, right? We could use this. Yeah, that was maybe something that I should have written. And here it's 1 over 0, which is infinity. So that's where the definition of the delta function comes from. And this is kind of how you should imagine it. So if you want to have something in exactly one point, you multiply it with a delta function, and that's what we're going to demonstrate now for the end of the video. So we said that the integral of delta of x is, this can be written as 1 or 0, depending on how far we go from. So if we go from minus infinity to some t, okay? Let's have a look at that. So we're integrating this one. This is delta of x. This is delta of x. And we're integrating from minus infinity to some variable t. Okay? Now t could be anywhere on the real line. This could be the t-axis. Or, well, this is the x-axis, but we pick t from the real line. And now t could be before delta x or after delta of x, right? Now, if it's before delta of x, we're going to integrate from minus infinity to something before delta x. We're not going to cover anything, so that's 0. We don't cover the delta function. So it's 0 when t is less than 0. And it's equal to 1 if we manage to grab the delta function. So if t is 0 or anywhere else, then this integral is a 1. So the integral of delta of x is this function. Maybe you've heard of it. It's the Heaviside function, the step function. But this is not very relevant to us right now. So if t is greater than or equal to 0, the integral of the delta function is 1. And of course, if we integrate over the whole domain, in this case, it's just r. If we integrate over all of r, we get 1. Okay, which would mean that t is infinity, right? And now, let's see what happens when we integrate a function with multiplied by the delta function. So this is something that's then written as a correlation later. Now, of course, by translation, delta of x minus a would be drawn like this, right? So if this is a, then delta of x minus a is this distribution. So it's non-zero only at a, that's when it's infinity, and it's 0 everywhere else. Okay. So now if I take a function, f of x, okay, and I integrate it, so I have f of x, delta of x minus a. Let's say that I'm integrating over the whole interval. Let's just say r. Integral over r of f of x dx and the delta function. This is going to collapse us into the function's value at a. Why is that true? Well, imagine you have some function. This is f of x. And since you're multiplying it with delta of x minus a, that means that you're multiplying it with 0 at every point. Multiplying it with 0 at every point except for this point. And that's a, right? So at a is the only time that delta of x minus a is not 0. And then what happens in this integral is that it's equal to dx f of a delta of x minus a for this reason, that everywhere else it's 0, right? Remember what we had with this constant when we wrote 1 over 2a as the amplitude of the whole function. It's very similar to this. And now f of a can come out in front, right? So f of a r dx delta of x minus a, but we know this. We know that this is just 1, okay? You could show that this is 1, even if you don't really understand it. You could show it by saying that x minus a is t, you know, just a simple substitution, dx equals dt, so the integral becomes dt of delta t, and this is just 1 by definition. So it ends up being f of a, which we got. Okay, well, this is kind of the introduction to the delta function. Next time I want to show why the delta function is the identity operator of Fourier transform, and then we'll define it like that as well and see if they match. Okay, thank you guys for watching. Bye-bye.